Hi, we're the UCCS Mechanical Engineering group that worked with Global Livingston Institute. My name is Crystal Corbally.
I'm Katarina Reynolds.
I'm Charlie Kiefer.
I'm Joseph Barron.
And I'm Denzel Frier.
Global Livingston Institute is an organization that is based out of Denver, Colorado. GLI is dedicated to improving communities globally. Every year, they send nearly 300 students and community leaders to East Africa for a series of immersion experiences focused on education and job creation. Their mission statement is to educate students and community leaders on innovative approaches to international development and empower awareness, collaboration, conversations, and personal growth. They have the focus is to not fix Africa, but to listen and think about the experiences you are having with the people you meet and the communities you visit to help better the area.
So GLI came to us with a problem. Currently, the local farmers at Lake Bunyoni, which is in Uganda, don't have a safe and efficient way to store their crops, whether that's potatoes, beans, passion fruit, etc. So, by storing crops for longer, that allows their value to increase, which then increases their profits that the farmers are receiving. So, by creating a storage facility, we can allow the farmers to make more money, and then of course make sure that none of their crops go to waste. So we were tasked with creating this food storage facility for the farmers, for them to store these crops for extended periods of times that is relatively inexpensive and uses local materials and local labor. So this goes into our requirements, which is that we had to determine a certain storage capacity for the potatoes that we assumed would be stored. And this value would increase year by year due to the farmer increase. Then it would only use locally sourced materials due to the cost, as well as making the food storage facility cost effective for any farmer to build on their own. The building of the facility itself would include local labor, whether that's the farmers or local construction, and it would have some sort of environmental control to allow for the produce to have a longer shelf life. Additionally, finally, it would have some low to no energy lighting for the farmers to see where their crops are being stored.
Earlier this year, we had the opportunity to visit Uganda to go interact with the farmers and the customer to really understand the problem at hand. Before we got there, we had a design in mind, and when we got there after interacting with the farmers, the biggest changes that we made first was the location. Initially, we thought the model farm was going to be on the resort. But after interacting with the farmers, we realized that we really needed to change the location to the model farm where the farmers can go there at any time and really pick on which technology or design that they would like to implement on their farm. Also, now our design is is underground, very farmer focused. The materials are locally sourced, as mentioned earlier. The design scalability, the design is made in such a way that it can scale up, and we included certain aspects of it, like ventilation, to ensure climate in the design. The overall perspective of the entire project changed because now we realized how urgent the project and how important this would be for the farmers. Also, we saw where they're currently storing their food, and we see the need for the design now. Yes.
On this slide, you can see on the left the final design that the team came up with. The picture on the bottom shows the food storage facility actually implemented into a hillside, which is the plan for the final design of the food storage facility. The walls will be made of wood with a tin roof. There will be a tarp in between the dirt and the wood sides of the design. This will help with rainwater that will go down and land into the French drain that will be used for drainage. There are also 2 solar chimneys located on either side of the storage facility that will be used for cooling and ventilation. There will be the only source of lighting that we have implemented into our design will come from the doorway. There's also the opportunity to add a door and have the lighting only come when the door is open, or also being able to add, the farmers are able to add their own source of lighting that they choose. There will also be a table inside the food storage facility to hold lighter crops, such as beans or loose potatoes. Finally, there will be an implementation of pallets on the ground that can be used to keep potatoes off the ground when they're in a heavy sack, so that the farmers don't need to lift them from a higher location.
Our structure, we went with a 10-foot by 10-foot footprint that is 7 feet tall. Most lumber in the area comes in 10-foot sections. So by doing this, we have allowed for the building to have a significant reduction in cost. We are using a cellar design since the average temperature during the day is around 75 degrees Fahrenheit. Keeping the building out of direct sunlight will reduce the internal temperature of the facility, creating a better environment for the crops to be stored in. Using a green roof, it, as seen in the picture next in the slide, it's a natural source of insulation for the building. It's cost effective and it keeps the internal temperature low throughout the daytime since there's no direct sunlight hitting the roof of the building.
In order to increase the shelf life of our potatoes that we store in the crop storage facility, we created a ventilation system that uses a solar chimney and a passive cooling system. The solar chimney is, as you see in the slide, 2 black painted PVC pipes that run from the top of the storage facility out to the atmosphere. These pipes attract the heat, the sun from, or they heat up from the sun, and this heats the air, and the air rises within the PVC pipes, which creates a low pressure zone, and it draws air out of the crop storage facility. This pressure difference then has air sucked through the passive cooling pipes, which are shown in the bottom right of the picture, and this draws air from the outside environment and runs it through cool dirt and cools the air before it gets released into the storage facility. For our senior design project, we were tasked to design this crop storage facility, so we did not have an actual product. So to prove that our design worked, we did various calculations to ensure that it was structurally sound and that all concepts achieved our engineering requirements. Solar chimney calculations were done to ensure that the solar chimneys that would be installed would be large enough to ventilate all the air out of the storage facility in a adequate time. Beam load calculations were done on the roof of the storage facility to ensure that additional weight from rain or even the additional weight of a person standing on the green roof would not break the storage facility. Surcharge loads were performed to determine whether the wood could withstand the surcharge loads from the soil in the area and whether land shifts would put too much weight or would apply loads, too great of loads onto the structure. And then we investigated various anchoring situations, or anchoring with cellar designs, and we determined that it was not necessary to anchor our design.
With all that, we saw a couple places where we can improve upon the current design. Currently, the design is made out of wood and very sustainable and very cost-effective materials, but we see that with just a little bit more money, we can upgrade the whole facility to a cement or concrete to improve current ventilation and cooling systems. Also, currently, we designed the facility to accommodate for a prediction of how much the farmers can harvest in the next couple of years. We see an opportunity for actually enlarging the current footprint of the storage facility underground, since there's a lot of space, and this will allow the farmers to store even more crops.
Finally, we'd like to thank our sponsor, GLI, for letting us solve this problem and give them a design. We'd also like to thank the Green Action Fund and the UCCS Mechanical Engineering Department for allowing us to go on this great trip to Africa. Finally, we'd like to thank the Ntusi Resort that allowed us to stay there and accommodate our visit.
Hello, and welcome to the Jabil weight counting final presentation by the UCCS design team. My name is Scott Jensen. Also working on the project is Sumya Kumar, Lauren Moen, Dylan O'Neill, and Sean Saul.
The project is for Jabil, which is a manufacturing company around the world. Specifically, this location is in Monument, Colorado, which specializes in medical screws. Our job was to identify factors that could be contributing to weight counting discrepancies. When screws are manufactured, they are then weighed on scales, and the scales produce a count, which enables Jabil to determine the amount of screws in a specific lot size.
As these screws come off the machine, they are weighed at various steps throughout the process. Occasionally, the count will be off from a previous 100% verification process. This process is extremely time consuming and costly. A lot of times it ends up in scrapping the entire lot. When they have lots with 50 to 1,000 screws and the price of a screw varying with roughly an average of $50 a screw, it can be extremely cost consuming. Through initial investigations, we toured the site multiple times. We also conducted interviews with both stakeholders and various employees on the floor, and we noticed a couple of different things. The first one being that the scale setup and the stand configurations varied at each weight station. So even though a screw went through multiple stations, it saw various scales and various configurations. The other thing that we noticed was that the process itself is left to operators' discretion and varies between operators. With those factors and others observed, we decided that an 8 factorial DOE would be the best way to explore the weight counting discrepancies that we saw in the facility. The first two that we want to talk about are the scale capacity and the initial count setup. So initially, we noticed that there was 12 kilogram, 5 kilogram, and 2 kilogram scales located throughout the facility. We decided for this specific project to only focus on the 12 and 5 kilogram scales, because the 2 kilogram scales were mainly only located over in the shipping area and weren't used on the floor. We also decided to look at the initial count setup. So some operators initially put 10 parts on the scale when establishing the count, whereas other operators put 25.
The third factor the team decided to investigate was part condition. The team noticed through their on-site investigations that as the screws come off of the machines, they have oil and grease, and the team determined that this must add to the weight discrepancies seen by the final results on the scales. So the team will of that air produced from the oil and burrs remaining on each part. Another factor investigated was scale configuration. As the team witnessed multiple weight counts being performed, they noticed that some of the scales were out of tolerance, meaning they were unbalanced. The team recognized that this could potentially cause weight counting discrepancies seen on a day-to-day basis, so they decided to include this factor in their DOE to see the magnitude of air produced from scale tolerances.
Enclosure and stand type were two more factors that affected the weight count. As the team walked through the Jabil plant, we found different enclosures. In some cases, there was no enclosure. In other cases, there was half a door, and in one instance, there was a cloth. We determined that airflow would affect the weight count as the plant has multiple fans that produce airflow, especially during the summer. The team noticed that the deburring machine produced a large number of vibrations right next to one of the scales being used, which could affect the weight count due to the scale sensitivity. A number of stands had isolation blocks attached, while some stands had wheels attached and a few only had a piece of cardboard attached to the bottom, which we figured would affect the weight count as only the isolation blocks reduce the impact on vibrations. We estimated early on that a full door with hinges would reduce the effects of airflow the most. The team received an NC report from Jabil detailing exactly which screws were resulting in a weight counting error, and we found that the following screws appeared a number of times. From family A, the titanium 503104 3.9 millimeter screw. From family B, stainless steel 21124 24 millimeter stainless steel screw. Batch sizes of 393 screws statistically covered the range of screws which are counted at Jabil.
In order to test the impact that the previous 8 factors had on the weight counting accuracy at Jabil, an online software called Minitab was utilized to create a design of experiments, commonly referred to as a DOE. And through this DOE, we were able to test those factors and determine any correlations between the factors or any individual impacts that those factors had on the accuracy of weight counting. From those results, we were able to obtain a couple very valuable results. The first one was that screw cleanliness, which was our factor D, was by far the largest factor contributing to error in final count. This was a result of the small screws not being able to be accurately counted when coated in oil. This was also this was also seen in regards to the large screws as well. The second result that we were able to determine was the initial count size, which we had called factor E. This had little to no correlation to count accuracy, which was very interesting and unique and went against what we originally hypothesized. It was determined that when performing the tests, the initial count size, whether it be 10 or 25 screws, both yielded similar results. The third result that we obtained was that the scale capacity, factor F, was discovered that the small screws were not able to be weighed on the 12 kilogram scale. This was due to them being so light that their mass was not enough to be able to actually trigger the scale, and resulted in us not being able to obtain an accurate reading or even a reading at all. The last conclusion that we obtained from this initial DOE was that scale configuration and cleanliness also showed strong correlation. When looking back at these 4 results that we obtained, we determined that a second DOE needed to be tested in order to further investigate some of the factors that returned insufficient evidence and insufficient data for us to draw conclusions from. We determined that in the second DOE, we would keep screw cleanliness, initial count size, and scale configuration all fixed at one possible configuration. So for screw cleanliness, all screws were to be weighed clean. For initial count size, since both 25 and 10 yielded similar results, we were only going to test 10 screws because that makes it easier for the operators to accurately count, which is a huge, like if they inaccurately count the initial 10 screws, then the whole rest of the count will be off. So that was maintained at 10 screws. The scale configuration was also fixed because it was determined that due to manufacturer requirements, the scales should be utilized in a level state. So they will be set up in the configuration where their bubble is within tolerance of the level state of the scale. In the second DOE, it was a 4-factorial DOE. So airflow, vibration, stand configuration, and closure were tested. From this testing, it was determined that screw type and scale capacity actually had the largest impact on weight counting accuracy. This just shows that we needed to test the screws on the appropriate scale. In order to also see more in depth some of the other effects that the factors had, the small and large DOEs, sections of the DOE were broken out and analyzed independently. The most conclusions were able to be drawn from the small DOE, which the results are shown on the right half side of the screen. It shows that airflow and enclosure, factor A and factor C respectively, had the largest impact on the accuracy of the weight counts for the small screws. When the screws were being tested and the airflow was placed directly on the scale, it experienced both high and low counts. As seen in the table, you can see that counts were experienced of 19 less than what the actual number of screws in the lot was, and 58 more than what the actual count in the lot was. This was due to the airflow and closure, as you can see in row 1 and the final row. You can see that in the enclosure, there was no door and high airflow in both the last row and the first row, which were both the highest difference away from the actual weight count that we were shooting for. It also was as a result of vibrations, which you can see in the final row where there was no isolation blocks and high vibrations, which resulted in 58 extra screws being counted than what were actually supposed to be there.
The biggest takeaway in our studies was the lack of a standard operating process through Jabil's weight counting procedure. A standard operating procedure needed to be in place, tailored to the screws being weighed. Smaller screws should be weighed clean with a low capacity, high resolution scale, and larger screws should be weighed clean with a high capacity, low resolution scales. Operator miscounts should be considered, and action should be taken to mitigate these. Some physical solutions could potentially be a trough that helps easily preload 10 screws for the initial count. Isolation blocks and full enclosures should be implemented on all weight stations to minimize the effects of airflow and vibration. And scales should be confirmed to be in tolerance before counting, as opposed to the 6-month calibrations that are currently performed. Lastly, we want to thank John Tebby and the Jabil team for allowing us to be a part of this project and helping us with all the experience we've gained through this opportunity. Thank you.
My name is Kelly Castrita, and I'll introduce the sponsor as well as present some background information about our senior design project, LRU Senior Box. Linköping University, also known as LIU, reached out to UCCS as a sponsor for the project for the LIU Formula Student Team. The LIU team is made up of several members who work on various tasks to include electronics, vehicle dynamics, HR, and business engineering. The LIU team designs, builds, tests their vehicles for Society of Automotive Engineers, or SAE, collegiate competitions. An example of LIU's vehicles is depicted in the accompanying picture. The team competes in the Formula Division of SAE. SAE is a collegiate level organization in which universities around the world compete in various divisions focused on various goals for vehicle design. These divisions include aero design, auto drive, formula electric, and hybrid formula and super mileage. SAE not only hosts the various competitions previously mentioned, but they set the regulations for each division to ensure a fair competition. While these competitions are held around the globe, the LAU team can only participate in those around Europe. The primary focus and design for the Formula Division is to maximize downforce on the vehicle while being as lightweight as possible. This emphasis on being lightweight will feed into the problem presented. The next speaker of the presentation, Riley, will discuss this problem.
Thank you, Kelly. My name is Riley Strency, and the problem addressed for our group was that their previous supplier no longer provided the part for their connection to use in their design, and they looked for an external contractor that could provide for this design. This overall halted the production of preferred regulated ZRAC for competition and the forward progress for racing in the upcoming competitions. They needed to build their own or buy a new one that was easy to manufacture in their shop located at LIU. This was to not require any unnecessary spending of money to build and was able to be built in-house. The external contractor was located at UCCS and enlisted us 5 for this similar design requirements and parameters. They wanted the design as close to the ZRAC specification given, but with some modifications regarding the connection to the column. The splint part of the steering box was the hard part to manufacture, and the new design should be made that can be easily integrated in the current design. The simplified connection to the steering column that can be made in workshop for future racing was necessary. Because of the competition to adhere to the FSAE guidelines for racing, all these requirements need to be met in the design. The design parameters were varied minimally except for the connection to the steering column. Finally, the reported progress to the design concluded to be expected for final authentication. Next is Alex.
Hello, my name is Alexander Huey, and I'm going to talk about the overall design of the steering box. For the required steering capabilities, a simple, lightweight rack and pinion design was used. In this design, a single gear acted as the pinion to drive the rack. The rack produced the necessary translational movement from the rotational input of the pinion and was connected to a strut on either side via studs. Each strut was fixed to a clevis on the opposite end using a small bolt. Each clevis was to be fixed to tie rods to transfer the motion of the rack to the wheels. The struts were designed to be fitted with rubber O-rings to be used as a bump stop to prevent damage between the clevis and the case. This bump stop also limited the maximum travel distance of the rack. This travel distance was adjusted by adding or removing or using larger or smaller O-rings. Bearings at each end of the case were used to ensure the struts moved freely and to provide support, which prevented undesirable lateral movement of the struts. The rack was held in position using a saddle, which only allowed for axial movement of the rack. Minor adjustments to the position of the rack could be done externally by raising or lowering the saddle using 2 bolts. The shaft and the pinion were held using 2 bearings, which allowed the shaft to rotate without any lateral or axial movement. These bearings also oriented the pinion for minimum play with the rack. The case was designed in 2 halves, which were then bolted together. Mounting points for the case were based off of the design of the chassis. The steering shaft connects to the pinion by mating 2 faces with shoulder bolts. Kyle Jocelyn will be outlining the connection for the steering shaft and its options in this next section.
Hi, my name is Kyle Jocelyn, and I'm going to be talking about the connection design. The main focus of this project was to design a new connection between the steering box and the steering wheel. It had to be quick and easy to separate from the chassis without cutting or breaking anything. 4 designs were evaluated. They were all compared based on weight, strength, longevity, cost, and manufacturability. A simpler design was chosen, but after discussion with the sponsor, we decided to go with a different design shown in the picture on this slide. This was done because of longevity concerns. One half of this connection slides into the steering column, which is in turn connected to the steering wheel. The other half slides into the steering box. The other half connects into the pinion by a set screw. The threads for this set screw can be seen on the shaft in the picture. Each half of the connection has a face that aligns with the face on the other half. They are connected together using 3 bolts and 3 nylock nuts. We will be delivering LIU 2 different options for the half that connects to the steering column. They can choose whichever one they would prefer to use more. The first option is steel. This part can be welded to their steering column, which is their preferred connection method. The second option is to have an aluminum piece, which is about 10 grams lighter, but it will be expected to have a shorter lifespan. With this connection design, all the specifications requested by LIU have been met. Now I'm going to hand it over to Taylor to talk about the testing.
Hi, my name is Taylor Clifton, and I'll be going over some of our testing methods and why we chose to do so. Some of our main requirements included the following. First of all, the strength of the rack. It must have been able to withstand a 6,600 Newton axial load and also be able to withstand a cyclic loading of a maximum operational torque of 15 Newton meters. During our testing, when we conducted these tests, we applied a 40 Newton meter force to include a factor of safety. In order to test minimal play, or I'm sorry, in order to meet the minimal play requirement, FSAE required that less than 6 degrees of motion occur before axial movement. LIU requested that we reduce this to 3 degrees of play. It also must be lightweight and weigh less than 430 grams and must also meet all FSAE requirements. Some of the methods we used for this were for the strength requirements, we tested the parts in SolidWorks using a finite element analysis and cyclic loading features. For the play of the rack, we 3D printed parts and visually inspected how they work together, as seen in the picture to the left. Mathematical analysis was also used for some of the testing to ensure that all testing done in SolidWorks was done correctly. We were able to meet all of the requirements that LIU provided us except for the weight, which an agreement was met with LIU to proceed, as we would rather sacrifice weight in order to ensure that the rack is strong enough to survive the conditions met during a racing environment. Thank you for listening to our presentation today.
Hello, everybody. Thank you for joining us today. We're going to be going over the real-time machine learning sensor algorithms on embedded hardware design project. We are the Northrop Grumman team, and this is part of the MAE 4510 senior design class. So I'll go ahead and get started. Next slide. My name's Richard Womack. I'm the team lead. I assisted Judavin with the algorithm side of things. We worked on developing that, and I'm a mechanical engineering major.
I'm Judavin. I've also worked on the algorithm with Ricky, and I'm mechanical engineering major.
I'm Tanner. I'm the spokesperson for the project. I assisted with the design of the graphical user interface, and I'm also a mechanical engineer.
I am Michael Tovey. I helped with documentation and assisted Tanner with the GUI, also a mechanical engineer.
I'm Christian, worked on research and hardware, and I am also a mechanical engineer.
I'm Lin. I'm Zhen Yulin. I'm doing the research, and my major is mechanical engineering.
Ready. So for the agenda of this presentation, we're going to be going over an introduction to the project, basically what Northrop Grumman came to us and asked what we were going to be doing. Then we'll be going over the design requirements that the senior design team came up with. That's basically everything that the project has to fulfill in order for it to be successful. We'll talk about the finalized design, so what we came up with in order to solve this problem. We'll go into a little bit of the algorithm structure just to cover our basis of this is how many layers we had, this is how many outputs we had, and then from there we're going to go into our graphical user interface, which is how we're going to interact with the customer. After that, we're going to go over the test results to show that the model was working as we had intended it to and show that it was a success. After that, we're going to cover some of our project complications, some of the issues we ran into, and talk a little bit about how we fixed those issues. After that, we're going to do a quick wrap-up conclusion, everything that the project became and everything that it was. And then we'll go on into some other possible solutions for improvements of the project. So, next slide.
The senior design team was sponsored by Northrop Grumman, one of the leaders in defense and aerospace development. We were tasked with designing a vehicle recognition software that had to balance processing power with identification time. The system was designed for deployment on an aerospace vehicle or ground surveillance systems. Project requirements on the following slides were agreed upon by Northrop Grumman and the senior design team. Next slide.
For the senior design requirement, based on the project requirements, the team developed 6 different categories for the requirement. They are DA, data acquisition, HW, hardware, SW, software, UI, user interface, A, algorithm, and T for test. For the most important part is the DA. The system should to identify the car from the different angle around the body of the vehicle. To set a baseline for the hardware and software requirements. To set a baseline hardware and software requirements for algorithm to run, our team came out H1 to H3 and SW1 to SW4. Next slide. UI, user interface 1, is based on the requirement from the Northrop. So the senior design team should build the user interface to display the vehicle's type, identify the time to identify the car, and the confidence distribution on the user interface. Also for the algorithm, our system can identify sedan, truck, SUV, motorcycle, van, and bus. For testing, the most important part is our algorithm should be identify vehicles type in less than 1 second, and the accuracy should be higher than 80%. Next slide.
Okay, for our final design, we decided to go with a convolutional neural network, or CNN, that uses the supervised machine learning method. For the supervised method, the datasets are grouped into 6 folders for the 6 classes: bus, car, motorcycle, SUV, van, and truck. This flow diagram shows the general convolutional neural network diagram that was used for this project. For the model structure, it is divided into an input layer with 3 hidden layers, with the last hidden layer being a dense layer and an output layer. Among these layers, 2D convolution, or conv2D, was used along with the ReLU activation function and max pooling functions. These functions then go into the last dense function, which activates the softmax functions, which gives the probabilities for the image classification. Over here on the output shape column, you can see that it loses an X amount of dimensions depending on where you're at. This is because of how each function behaves. And over here it says none, because it does not have a predefined number so that the model is flexible. Only the conv2D and dense functions have a parameter number, since these are the only functions that have learnable parameters shown in the last column of the chart. And over here at the bottom, you can see the sum of the parameter numbers.
A graphical user interface was created that allows a user to select an image of a vehicle. The Select Image button opens a file explorer that contains a data set of the 6 classes of vehicles used. Once run, the interface will display the vehicle type, the AASHTO class, the algorithm's confidence, and the runtime. The About button on the right of The About button on the right will open the user manual and instructions for installing the graphical user interface. Next slide.
When looking at the testing confusion matrices that we got after running our algorithm, you can see we have an accuracy on the first line of 89.7%, which is nearly 10% above what we were shooting for as a parameter from Northrop Grumman. Then we have the confusion matrix, which identifies all 6 rows with the 6 bus, car, motorcycle, SUV, truck, and van. The diagonal numbers that are high in that matrix show how many vehicles were identified correctly, with the corresponding 1 through 6 column identifying the wrong. When looking at precision, recall, F1 score, and support, precision is the number of correctly identified images in each class. Recall gives an idea of how often the algorithm predicts the true value. F1 score is a weighted harmonic mean between the precision and recall. And support is the number of images in each class. As I said before, we had a testing accuracy of 89.7%. This is reflected in the rounded up macro and weighted average of the test confusion matrix. Next slide. We did have some project complications during this entire project. The first being the initial training and testing accuracy was less than 50%. This was meaning that we were not hitting our goal, and this was fixed by mixing all of our data sets, testing, validation, and the learning. And that was done to normalize the collected data set. Also, during that time, filters were changed, which changed the algorithm a little bit. Then the vehicles were being misidentified when the algorithm was increased from 3 to 6. The prototype code started with just 3 vehicles, and then we pushed out to 6, which we were normally wanting to do as a requirement through Northrop. This was again fixed by normalizing the data sets. Another problem we ran into was the GUI was misidentifying outputs from the classification algorithm. And during all the fixing and prepping of the model, this let the GUI finally output the correct classification for the vehicles that were being identified. Next slide.
So in conclusion, the senior design team was assigned by Northrop Grumman to develop an algorithm capable of identifying 6 different classes of vehicles. The algorithm was able to obtain an average accuracy of 89% with an average identification time of less than 0.5 seconds. And we also developed a GUI for it. Next slide, please. Although the project requirements were met, improvements still can be made for the algorithm if more time was available to work on the project. The main focus on improvements is on accuracy, and these improvements include grayscaling the images, adding more layers to the convolutional neural network, modifying the kernel sizes, changing resolution of the images, modifying the number of batch sizes, and using different optimizers. Next slide, please. And this concludes our presentation.
Hey, thank you for joining us today. This is the Podium Senior Design Team. I'd like to introduce everyone. Myself, Ryan Seifert-Meisman, Micah Mesward, Emily Ebby, Kevin Brown, and Sean Kokenauer. Special thanks to Blake Egan for this opportunity sponsoring this project. The objective of the senior design project was to design a sorting machine capable of sorting pellets in order to reduce scrap and optimize the design process or production process. The deliverables were to give Blake a complete bill of materials, CAD models provided in solid part and solid assembly files, design and machine drawings provided in solid drawing and PDF files, a functioning proof of concept, user safety manual, and a maintenance manual. Currently, Podium controls the pellet masses to 50 milligrams as industry standard, using statistical analysis to control each batch. With this senior design project, we will hold the pellets to 5 milligrams, and a superior product line will be created using this automated process. The quality of the product depends on the weight of the pellet as well as the shape, but in this design, we use the weight of the pellet as the controlling factor, as a light or heavy pellet changes the shape.
After concept generation, concepts for each section were analyzed using design matrices. Matrices for the unloading, sorting, and loading sections are shown here. One concept was selected as the datum, and all other concepts were analyzed against the datum to determine whether it meets each requirement better or worse than the datum. This was done iteratively, changing the datum each time to determine the best concept for each section. For our unloading matrix on the far right, you can see after doing our original analysis, the results were too close, so we had to create priorities where we weighed each requirement based on the necessity of them to determine which one would have the best ability to meet each requirement after being weighed. From those requirements, we came up with this original system design. It utilizes a vibratory plate to bring the pellets to a step feeder. This feeds the pellets into the cogwheel, which individually weighs 10 pellets simultaneously. They then enter the servo selectors, which adjust the path of the pellet to the correctly sorted bin based off pellet weight. After our conceptual design review, Podium decided to source a vibratory feeder, which changed our project requirements by eliminating the first part of our design and left us with from the cogwheel all the way on. The first part of our design is the cogwheel. The cogwheel separates pellets individually for weighing, as well as placing the pellet on the scale and removing it off the scale after being weighed. The first one on the left is our initial design, which just has an arbitrary number of holes. On the second part on the right is our final design, which contains 20 holes, giving us the ideal step size for our stepper motor specifications.
In order to sort the pellets after it has been weighed, we needed a way to select a path to the appropriate bin. At first, we decided on servo-driven selectors that rotated horizontally, where the pellets would slide into tubes that would connect to the appropriate bin. However, once we began designing the system, we realized this would require 50 tube paths, which was unreasonable for the design. Our solution for this issue ended up consisting of 5 large planes that are the output of all 10 selectors that rotate vertically instead of horizontally. We wanted to simplify the downstream path of the pellets as much as possible with this solution. Each plane connects to a single flexible tube that leads the pellets to the appropriate bin. This design allows for minimal risk of damage to the pellets while allowing for the fast sorting time required by the system. The conceptual design cost approximation was based on our research of required components and manufacturing. We also estimated for miscellaneous materials to serve as wiggle room for the project as it developed. Our initial estimation was around 10,000, which was agreed upon by the project sponsor. Since we had some design changes between our concept and our final design, the cost estimation changed. The largest change was the feeding system of the pellets. Our project sponsor suggested outsourcing the system, which drastically increased our approximated cost. Due to the increased costs of the overall system, our sponsor recommended having the rest of the system cost to be within a reasonable value. And he was relatively flexible with the overall cost. He said that as long as it didn't have the price tag of a Ferrari, he would be happy.
All model creation was performed in SOLIDWORKS CAD software. A test model was designed, 3D printed, and built, and a one-channel proof of concept was also modeled, 3D printed, and built. Both of these were used to test certain functions and validate the overall concept. Some of those functions include servo functionality, coding validation, fit of pellets in the cogwheel, and angles of the selectors and transport trays. All files were provided to Podium in the appropriate file formats of part, assembly, and drawing formats from SOLIDWORKS, as well as PDFs for the drawings and STL files were also provided for anything that needed to be 3D printed. Any part requiring machining has drawings with detailed dimensions so that they can be correctly manufactured. All subassembly drawings, as well as the final unit drawing, have exploded views with bill of materials and balloons. And notes were also added to simplify the assembly process for Blake at Podium.
On the left, we have a video of our functioning proof of concept. This was used for a variety of things that turned out to be very beneficial. Primarily, it was used for testing of the different hardware components as well as the electrical system and the software. Through the course of testing, we made a couple adjustments to the hardware. It allowed us to refine the design a little bit more. Due to these adjustments, some of the parts will be usable in the final design, however, some will not be. The main three mechanical parts of the system that we used this for validation were the cogwheel feeding and motion, the selector motion and angles, and the transport system consistency. Through the course of these tests, we came out with a resulting 99.33% confidence in the design. It also resulted in a pellet per hour rate of 2,351, which resulted in us being able to sort 211,590 pellets in 9 hours, which exceeded our requirement of needing to be able to sort 200,000 pellets a day. Through the course of this testing, we also discovered an issue with the load cell we were using to weigh the pellets. So as we were testing, we came to the unfortunate realization that the load cells we had been using and working with would not provide the accuracy that we needed. The unfortunate part about this was that we found out 2 weeks from the end of the project. As a result, we did not have much time to work with to find a solution. So after a couple meetings, emergency meetings, we came to a suggested course of action, which Podium agreed to very graciously, where scales will be used in the future to provide the accuracy needed. However, due to the time, we will not be integrating them into the system. The technology, though, underlying the laboratory scales as opposed to load cells are fairly similar, so the integration of the scales into the rest of the system will be relatively simple. So for the coding, since we were using an Arduino to run the whole machine, we logically used the Arduino IDE to program it, which is very similar to C, which has a lot of similarities to MATLAB. It's allowed for several of our team members to be able to program pretty quickly without having to learn too much. To run the system properly, we also needed a few third-party libraries integrated into the code so that we could properly control the servos and get readings from the scales. In the code, there were three main sections in the structure. There was the first section that was a declaration of global variables and parameters, as well as the inclusion of those third-party libraries. Second section was the setup of the communication from the Arduino to the sensors, the actuators, as well as the computer for displaying results. And the final section was the execution portion, really the heartbeat of the code, giving all the commands, reading the sensors, and performing logical checks to see if jams had occurred from sensor readings.
So after the final meeting with Blake, it was determined that this is still a successful outcome for the project, as the proof of concept still shows that the code and mechanical design can be used to sort the pellets in order to reduce the scrap and optimize the production process, as long as the load cell was switched out for a scale. I wanted to thank Blake once again for this opportunity as an educational experience and our school sponsor. If any of you have any questions, please feel free to join us in our breakout session.
Hello, my name is Paul Park. I'm the lead for the senior design project. The focus of this project was a rotating detonation engine. The team consists of Long Tran, Noble Kilman, Carl Rees, Marshall Hoyt, and I. The sponsor for the project was Dr. Matt Quinlan. The rotating detonation engine is a device that utilizes a detonation within the annulus ring to ignite fuel and generate thrust. The detonation produces high thrust for low fuel usage, making it efficient compared to other rocket engines. All RDEs are currently under testing and prototyping phase and are not currently in use. The problems that come from a RDE, the rotating detonation engine, are incomplete fuel mixing within the engine, viscous force in the annulus ring, and shock reflections that occur that go opposite to the direction of flow. These problems pose a serious issue to the effectiveness of the design, and solving these problems is what will make the rotating detonation engine a viable engine.
To solve a lot of these problems with the RDE, we focused our project on the knowledge generation around RDEs, the fuel mixtures, design choices made throughout other research, and anything that impacts the ineffectiveness of current RDEs. The things that we want to maximize are the design of a detonation tube, which would act as an igniter to the rotating detonation engine by creating a shock wave with accelerated flames. So we want to maximize the speed of that detonation, make it as fast as possible, and minimize any kinds of transverse shock reflections in the tube, taking advantage of the longitudinal shock reflections that will actually accelerate the flame as well.
As we moved through the course of our design, we had to adhere to certain requirements. It had to be able to actually transition a deflagration to a detonation wave, e.g. turn a rapid burn into an explosive combustion wave. While we'll momentarily discuss how we got to these design elements, over the course of our project, we finalized the following parameters within our detonation tube design.
So starting off with our probably most important parameter, the fuel and oxidizer, we chose H2 and air at a 29.6% fuel concentration level. This gave us an estimated detonation cell size of 12 millimeters. Moving on, we have a material that we chose of 304-316 grade stainless steel. This was for the primary casing and the blockages within the design. Next, to ensure deflagration and detonation was achieved, we installed top and bottom obstacles within the tube. This also allowed for potential for staggered or symmetrical. Going over some rough dimensions, or the most important dimensions, we have the tube, including the mixing chamber, was 268 millimeters long. 240 of those were the detonation tube, and the inner diameter was 24 millimeters. The obstacle spacing within would be at a range of 1 to 2.5 times the diameter, and a blockage ratio of 0.4 to 0.6. Other dimensions can be seen in the model below, and are also included in the report.
Additionally, we had designed the fuel and oxidizer inlets, the mixing chamber size and shape, the spark plug ignition, and general geometry based on the existing research and testing documents available, and the consultation of machinists and the feasibility and manufacturability.
To begin the process of finalizing the detonation tube, several research topics were distributed across the team. The fuel and oxidizer, material, deflagration to detonation transition, and dimensions were key points of research and design.
Detonation cell size, a phenomenon vitally important to detonation tube design, is physically represented in these kinds of tubes by the diamond-shaped scorch mark pattern that's observable on the interior after detonation wave has moved through it. This is integral for a proper detonation to occur. So, in our design, we found that many elements ultimately relied on detonation cell size, elements such as the diameter, blockage spacing, and length. Knowing the relative size of the tube that we wanted to design, we analyzed multiple reactants for their effect on detonation cell size. The considerations for fuels and oxidizers can be seen here. We had to balance the reactivity of these possibilities with detonation cell size effect on detonation tube size itself, avoiding combinations too dangerous like H2 and O2, and combinations too large of a detonation cell size like methane and air. Ultimately, we landed on H2 and air at stoichiometric levels, approximately 29.6% fuel concentration, which thusly allowed us to move forward with the rest of our design.
For the material chosen, we landed on using grade 304 or 316 stainless steel. Originally, we considered other materials like superalloys due to their being common in other aerospace structures. They have excellent heat resistance, but were often expensive. It was also determined that it would be unnecessary because the detonation tube would only be under this extreme temperature for a split second. So this allowed us to just use a low-grade steel. It would be sufficient in handling the temperature for the short duration, as well as allowing for better machinability.
So the method to ignite a rotating detonation rocket engine by use of shockwave is called a defragration to detonation transition. A small spark at the end of our tube will propagate through these obstacles, and shock waves and large pressure spikes within the obstacles will induce flame wave acceleration and create the detonation used to ignite the RDE. We considered a variety of different obstacle designs based both on research and idea generation throughout the team. And it was pretty easy to realize that simplifying the design is the most important part. This makes the machinability of the part much more achievable. We considered different ways that you would have to bore out solid tubes or fill in slotted sections of hollow tubes. Because of the limitations in resources for the team of focused on machinability, a simple design is desired for our detonation tube.
So the diameter of the tube was designed to be 24 millimeters based on the detonation cell size of the fuel and oxidizer chosen. From there, the next focal point were the obstacles that had to be installed in the detonation tube. So the obstacles that were implemented in the design served the purpose of inducing flame acceleration and allowed the detonation to occur much faster in the tube. In order to do so, the optimal blockage ratios were researched, considered, and calculated. The blockage ratios that were examined ranged between 40 to 60% of the cross-sectional area of the detonation tube. The amount of space was an important factor to consider because it was needed to have shock reflection in order to accelerate the flame. Smaller blockage ratios did not induce enough flame acceleration, and larger blockage ratios inhibited the detonation from occurring properly since it prevented the detonation from traveling from the detonation tube. After that, the distance between the obstacles had to be decided. Based on similar experiments, the optimal spacing for the optimal spacing was set to be 1 diameter apart, meaning they were 24 millimeters apart, or 2.5 diameters apart. Similar experiments indicated that this range allows for proper flame acceleration.
So as Sean mentioned before, we had 3 variables that we wanted further information on because we're in these ranges and we wanted the most optimal detonation tube. And again, those 3 variables were blockage ratio, obstacle spacing, and our inner geometry. To do this, the team took on computational modeling. We wanted simulation software capable of combustion modeling so we could determine these 3 variables. We landed on a program called OpenFoam, which is an open source CFD toolbox. And it had the capabilities to allow for developers to customize their own numerical solvers. This was really the key for us. These numerical solvers included combustion solvers and were what we were going to take on to get our variables.
So the team designed variations of the detonation tube with a CAD model, changing the respective values such as blockage ratios and obstacle spacing, as Kyle mentioned before. But the important factor is that we saved everything as STL files under ASCII format because those were compatible with OpenFoam and the program systems. So values such as velocity, pressure, and temperature could be seen at different time instances. ParaView was an extension of the program to visualize the simulations on the design models made by the team. In order to set up simulation, mesh files were set to act as the environment around the model. The mesh files had definitive boundaries written so that they encompassed the entire model. The vertices represented the dimensions of the system, and they acted as the boundaries of the system. So it outlines the inlet and the outlet of the system to designate the flow travel through the simulation. The rest of the surfaces of the system were designed as walls so that the flow travel does not escape through the surfaces, but only through the inlet and the outlet. Once the boundaries were set, the simulation could start and the visuals could be seen on ParaView. It was a difficult process to get where the team reached, so some team members set up a user guide.
Yeah, so as Sean said, we gave you a little inside look on what we were doing in OpenFOAM. And along the way, we documented our findings and our processes in a user guide or user manual. We determined it necessary to create this user manual for two main reasons. First of all, OpenFOAM, although accessible, was very not user-friendly. This is often the case for open source software, but was far worse than we thought. Along with this, it runs in the Linux environment, and only very few members of the team were familiar with using Linux. These two issues combined made using OpenFOAM and progressing in it difficult, but hopefully the user guide aids this. The sponsor and potentially future users will be able to read through our guide and not only catch up to where we were very quickly, but also along the way, hopefully learn how to use OpenFOAM properly and efficiently use the Linux command line.
To summarize, the team generated knowledge on the design parameters of a detonation tube for a rotating detonation engine, the fuel and oxidizer, material, deflagration to detonation transition, and dimensions were selected through research and understanding of the engine and every single one of these parameters. The simulation intro was given and a clear path to a prototyping phase was made.
To move forward with this kind of project, as Kyle mentioned, there were a lot of obstacles in our way for completing simulations and getting an understanding of all the boundary conditions, the constants and zeros that would need to be applied to optimize obstacle spacing and blockage ratio. To determine these engineering parameters, we wanted to move forward with simulation, which would be the next step of the phase, to hopefully reduce the current learning curve for a future project or team that would pick up this project. That user guide is going to get you to a starting place and explain everything that we've learned so far. And going forward, you would hopefully move into a build phase that could be done in a UCCS laboratory, which could then move to testing and deeper understanding of REEs. Overall, we've focused on the knowledge generation of the rotating detonation rocket engine. And we want to thank our sponsor, Dr. Matthew Quinlan, for his time and effort, and the advisory staff and the faculty for being there and offering guidance and walking us through this design process. I hope you've enjoyed the presentation then.
Hello, we are the engineering design team Racing Cows. My name is Garrett Weiss.
My name is Korsang Sherpa.
My name is Justin Zalewski.
I'm Kyle Profita.
And I'm Deshaun Alcock.
So, the problem that we were faced with was to design a device, mechanical device, which may be used by a dog owner to train against bad behavior. Many dogs behave poorly when the doorbell is rung, such as with running to the door and other hyperactive activities, such as barking and jumping. And so the goal is to provide a distraction in the form of treats whenever a doorbell is rung. Our secondary goal was to provide an effective installation and training manual for use with the device, such that any normal dog owner would be able to use. And training may only be accomplished through positive reinforcement methods. Some notable design specifications we were given was that the device must accommodate for dogs and treats of all sizes. Also, the device must have an affordable design with competitive pricing when compared with similar devices.
Following the problem description, we had a few interviews with dog owners and dog trainers regarding what kind of things that they like the product to accomplish. So based on that, we had a bunch of brainstorming sessions, and we came up with our initial design. So for that, we came up with a rectangular exterior holding a clear plastic treat storage device. We would use a motor to rotate the gear, and that would rotate the sphere. So we used a mechanical support, which is a motor for rotating the gear from a rotating gear. Okay, give me just a second.
Oh, you're good.
Okay. Can I continue now?
Yeah, go for it.
Okay. So we used a motor that would rotate the sphere, and hence it would be dispensing treats into the detachable plastic tray. We would use keyhole screws to connect the device to the wall, and the device would be powered by a wall socket, and the device would communicate to the doorbell through the wireless Bluetooth connection. So during the final stages, we were having some issues with our design because the spherical ball was having some issues. It was hard to attach it to the. It was hard to attach it to the casing while still rotating. It was difficult to cleaning, and so we had to make a few changes to the device. The changes were we would replace the spherical ball with a cylindrical device, and we would attach an auger to the base of the cylinder that would rotate with the help of a motor and hence dispense treat.
The final design of the device from the mechanical standpoint looks like the picture to the right. The material of the device will be low density polyurethane. This material is FDA approved, food safe, and dishwasher safe, which means it's food safe and dishwasher safe. The design is modular to keep the assembly and disassembly of the device simple, only having 6 parts in total for the full device. The device will also be easy to clean because of this modular design. The auger can be removed and put in the dishwasher, as well as this treat storage element, the tube, can also be put in the dishwasher. The tray can be sprayed with disinfectant and wiped clean. The device is pet safe due to the fact there's no pinch points. The auger is covered so the dog's nose does not get pinched, and it's height adjustable so that it can accommodate for different sized dogs by simply putting screws into the wall and hanging the device from those screws.
The next component was the electrical side of the final design. A lot of work had to go into the electrical as we had to interface with both a doorbell operating system and the device itself wirelessly. And that involved taking AC and rectifying it down to DC power, and also reducing that voltage in the device so that the Arduino development platform could sense when the doorbell is ringing and also be powered by it. We used a wireless Bluetooth connection because of the wide variety of wireless devices in a household that use radio frequencies, and we didn't want radio frequency interference to be an issue with this device. And so we went with dedicated Bluetooth connections. We also used the Arduino development platform, as I said before, for logic coding and sensing. This gave us the best platform to code on. It gave us a good working chip to do data processing of the signal and sending messages back and forth between the Bluetooth devices. and all of the wiring inside the component and the design for the electronic components had to be UL and CE compliant, which they are. This slide here is just an example of the wiring that was done on the device, where we had an Arduino that's powered by the AC unit in the top right, and that Arduino talks with the top left-hand corner with the Bluetooth device there, and it uses several rectifying diodes and resistors to step voltage up and down.
So to make sure our device solved the problem that our sponsor gave us, we did some tests. The first test was a Bluetooth test. So we tested in a 2,400 foot square foot home with an unfinished basement. It is 3 floors, and we tested from one corner to the other, and we didn't get any drop in connection. For our finite element analysis, to simulate how the device would be operating, we put a 5-pound force on the tray to simulate the dog grabbing for a treat with its nose, a 2-pound weight on the funnel to simulate 2 bags of treats being pushed on it, fixed locations at the keyhole screws because that's where the device is going to be attached. The backing had a rocker slider. We had cylindrical beams to simulate the screws that attach the top and the bottom of the device. We found out that the factor of safety was 20, which is really good. So we know that it's not going to fall apart. For the motor, we simulated a point mass 2.5 inches away from the base of the motor. We found out that the motor could spin the device with a factor of safety of 2. For the auger efficiency, we pushed the doorbell 10 times, and the treats were dispensed 9 out of those 10 times. So with these tests, we can conclude that our device solved the problem that our sponsor had for us.
Guys, I just wanted to give you guys an actual physical rundown of the physical prototype we made and show you guys it all working together with a mocked up doorbell system and everything. So if you look here, this is our makeshift secondary module board. This is what hooks up to your doorbell system with this black and white wire that hooks up to the end of this makeshift doorbell system here, which is run by this 20 or 16 volt transformer and this doorbell button on the front of the box. This all runs into this Arduino here and this Bluetooth module hooked up on the secondary board. And this Bluetooth module speaks to this Arduino and Bluetooth module inside the base of our treat dispensing device. This is just a mocked up motor due to the circumstances we're all in. I couldn't get a full-size NEMA 17 motor working, so this is just a makeshift motor and motor driver down there just to show this all working together. And this is all powered via a 12 volt power plug that comes out of the back of the device here. And I'm gonna go ahead, throw this all back together so I can show you guys a quick example of the whole device working. Back, this is the completely put together piece of device. I've got it plugged in to our 12 volt power supply in the back. We went ahead and plugged in our 12 volt power supply here. We're gonna throw some Cheerio, aka fake dog treats, into the device there. Then we're gonna come on over here to our doorbell. You can see that everything's powered up and working here. We're gonna go ahead and give the doorbell a push. We're gonna give it a couple seconds to transmit the signal, and you can see it starting to spin. Now we got some dog treats, not quite ready to come out yet. That's just because we just filled the device, but you guys get the gist of it. And I think that is a great example of our doorbell dog treat trainer. Thanks again, guys.
Hello, everyone. Thank you for chiming in and taking the time out of your day to listen to our presentation. We are the Raytheon Senior Design Team. Our team consists of Alex Buffmack, Dylan Copley, Bradley Pring, and last but not least, myself, Aaron Vestal. The world around us is driven by technology. The technology is constantly evolving, and often it evolves around the software used to operate it. For example, much of the software used in missile defense systems today was written in languages that aren't even around anymore, or whose designers and programmers are long retired. Coders also often leave their own footprint, so the codes can be very difficult to understand what they were meant to do. This is why we've been asked to help develop a process that would either automatically or manually take a free and open source code in C++ and model the software architecture as well as a high-level functional design, preferably while using the same tools Raytheon has available. This will hopefully allow some of us that aren't software engineers to understand the basic functionality of most codes. Alex will now elaborate on our process of finding a source code as well as developing our use cases.
To reiterate, the source code needed to meet two primary requirements. It had to be free and open source, and it had to be a system of separate scripts that interact with each other. Initially, we turned to online repositories like GitHub to find a suitable code. We narrowed it down to about 6 options and eventually decided on a code called Turn, which was a simple console-based game. However, once we started trying to analyze and work with the code, we ran into major issues that prevented us from progressing. At this point, we decided to use a code that I had been constructing as a personal project. It was similar to Turn in that it was a simple game and it met all of the requirements laid out by Raytheon. Once we had this new code fully written and ready to go, we moved on to begin our journey into code decomposition, which Brad will now share with you.
2 requirements from Raytheon for an IDE for this project are 1, it must be designed to run Java or C++. 2, there needs to be some version of UML modeling that's either built in or can receive a plugin containing a set of UML libraries. With the influence from Raytheon's POC, Eclipse was the highest and first consideration the team had for the IDE. When researching the packages to install, it was shortly realized Eclipse was primarily designed for Java, which, based on the code requirements, is acceptable. However, based on the codes already determined by Alex, it was decided to go find a plugin to adapt the IDE for the use with C++. After some additional challenges with the solution, the group was divided into 2 sections. One was to explore the other IDEs available as a backup, while the others were to continue pursuing Eclipse. NetBeans was shortly considered around this time. However, similar issues with Eclipse were surfacing, and the results in choosing this as an IDE are no longer being considered. Efforts were applied into research and development for a plugin, but were short-lasted since Visual Studios and Rhapsody were already being considered and looking much more promising this early on. Visual Studios is known for primarily being used for C++ editing, building, and debugging. However, there is also an automated decompiling feature. Being that Visual Studios is so widely used and popular, it was assumed that the decompiler was able to decompile to the level required for this project. Unfortunately, it was not. A major upset for the team, as this could have been the only software needed for this project. However, the senior design team is taking advantage of Visual Studio's great GUI along with the free trials to help edit the code developed by the team with ease. Using the developer version of Rhapsody comes with a built-in UML modeling library, a far more in-depth decompiler than anything previous, and a decent GUI system that makes C++ code easy to edit. It was without hesitation that this IDE will be used for this project. So far, the use cases have been manually built, but the senior design team is striving for a fully automated system of systems. Once properly formatted, Rhapsody has been used to automate, decompile the source codes, and use the manual created sequence and activity diagrams requested from Raytheon. Using the built-in class diagram functionality in Visual Studios, we have generated a diagram of all the included classes along with the relevant attributes and methods for each class. Lastly, another software used is Code to Flow. Code to Flow is a tool used for someone who is unfamiliar with a code's architecture and possibly language, and this creates a manual activity diagram that describes the flow of any use case. Given a legacy code, one could put each file into Code to Flow, which generates the step-by-step logic. Take some time to understand the process of the source code as a whole, and then track down the operation taken, as well as each function reference for any given case, which is all necessary information for the manual creation of a sequence diagram. Internally, one team member was also created a Python code that also acted as a high-level decomposition tool. Dylan?
Thanks, Brad. Well, one of the approaches made to accomplish full automation of the decomposition of C++ code was a custom-made Python script. And this approach was chosen because all of the reverse engineering tools that we had explored through Rhapsody, Star UML, Visual Studio, and other UML editors lack the ability to automatically decompose code in a simple plug-and-play application. In its development, we were able to achieve the same basic level functionality of other UML editors in terms of importing operations and attributes of CPP and H files by means of a string interpreter that would look for a common C++ functions and code. Ultimately, the effort into the contextualization and visualization of operations that would allow automatic activity in sequence diagrams was found to be outside the scope of the project, and instead, manual decomposition was chosen through Rhapsody. The diagrams made were sequence and activity diagrams. Sequence diagrams would show the flow of users' interactions and the interactions between objects in order to achieve those actions in a sequential order. Activity diagrams show the activities of each operation in the code and visualize the behavior of the system. This includes the operations, behavior, loops, conditional checks, and general behavior of an operation as it is executed. These diagrams are created manually in Rhapsody by referencing the source code line by line and including the appropriate objects that correctly model the execution occurrences. This process can be viewed in a couple short tutorial videos that document the step-by-step instructions of creating sequence and activity diagrams. Lastly, our final results that include our diagrams can be viewed in our final report. Now I'll pass it on to Aaron to wrap us up.
Thank you, Dylan, for elaborating a little bit more on that. So ultimately, we have documented the process of the full decomposition as well as all of the challenges and the resources that we used to face in our final report, as well as a screen capture that kind of outlines the process of creating these activity and sequence diagrams that we will be delivering to Raytheon as well as UCCS as part of this project. We want to thank Raytheon and UCCS for giving us the opportunity to diversify our own skill sets, as well as hopefully assist in the continued development of technology all around the globe. And of course, we also want to sincerely thank everybody that's been supporting us throughout the entirety of this project, because obviously it hasn't been easy, but we're extremely happy and proud of what we can present today. So thank you all very much. I hope everybody has a great rest of their evening.
Hello, our team developed a recoil mechanism for replica AN M2 Browning. We are Team Freedom Force, and our sponsor was the National Museum of World War II Aviation. Now, I will let the team members introduce themselves, and you can follow along by looking at the headshots on the right. Starting at the top right and moving clockwise, I'm Dylan Hansen.
I'm Thomas Schumann.
I'm Caden Blue.
I'm Thomas Cordova.
I'm Greg Salser.
And this is our presentation of our final design.
The National Museum of World War II Aviation has an emphasis on education. And for this purpose, they wanted to recreate the experience of a soldier in a tail gunner position of a bomber. And to this end, we wanted to design a 50 caliber machine gun. The exhibit needed to be fun, It needed to be interactive, needed to be educational, and as historically accurate as we could make the replica. It also needed to be variable recourse so children could use the exhibit. Next slide.
The team began this project with some preliminary research that involved looking into pre-existing solutions. Here we found the Acme Worldwide Gun Active Recoil System, which served as a full military training system. This, however, was extremely expensive and was only capable of full force recoil and not going lower. Devaric Air is also in development of a pneumatic solution, but similarly could not be adjusted down in recoil forces and was also quite expensive. Also, little is known about this as it's still in development. The team also looked into the forces required to recreate the recoil and used conservation of momentum to find those listed below. Next slide.
For our initial concept, we looked into creating a slide crank system driven by a motor that pushed a counterweight. After some research and development, the team found that there were no available counterweights that were the size and weight that we needed. Also, during the research stage, we found that the force-speed ratio needed for the motor was unachievable due to the weight that the motor needed to push. Because of these constraints, the team came to a consensus that we needed a different design to recreate the recoil system for our replica. Next slide.
Using the conservation of momentum was sound, but we had no actual data to support the recoil force of the M2. So we reached out to Fort Carson, and 277 Field Artillery generously hosted us and allowed us to come out to their range and record the mass of the machine gun and all equipment associated with firing, such as tripod, ammunition. We then hooked an accelerometer up to the machine gun and recorded data. Next slide.
Since a new approach was needed for our team, we did a trade study to narrow down our options. Our first cut option was an air cylinder system. It was cut because it would overheat while we were trying to get to the required RPM, and the equipment needed was just too cumbersome for the museum. Our second system that was cut was our vibrating motor system. This was because the vibrating motor was too big to fit into the receiver, and it wouldn't accurately recreate recoil. After looking at these, we decided that recreating recoil itself wasn't really achievable, so we moved to a handle displacement system that made it feel like recoil. Our initial concept for that was our linear servo motor. This went into further development, but was cut due to the motor being out of our price range. Our final system that we decided on was a rotary motor with a crank system. This system actually achieved all of our goals and was our final design. Next slide.
The preliminary design determined from the trade study initially was to use the linear servo motor. This achieved all the specifications in the most efficient way. This included being able to adjust the rate of fire and recoil on the fly with some programming, and it could be adjusted from 0 to full force. This design would also fit entirely within the receiver, requiring no external modifications to the replica. Unfortunately, this design was found to be far too expensive for the museum's budget of $1,500. In addition, this design was slightly limited on the rate of fire of only 600 rounds per minute rather than 800. For these reasons, the team moved to the critical design. Next slide.
For the critical design, the presented design was to have a rotary servo motor which drove a gear train that connected the linkage to the handle. This setup can be seen in the CAD model at the top right. The critical design utilized a low torque motor, which is the reason we were required to use a gear train. The gear train allowed us to take excess speed from the motor and transition it into additional torque to meet the required torque to move the handle. For this iteration, the linkage and the gear, neither the linkage at the gear connection or the handle connection had a rod end to mitigate that any misalignment. On the gear, you can see that the variable recoil slots have very little variation from the middle to the outside. This limited our variability, and we were only able to get down to about 76% of full force. Next slide, please.
For our final design, our primary improvements focused on revamping the entire system, starting with a change of a motor. This new motor is able to sustain a peak torque of over about 9.8 Newton meters. However, we will only be using a slight margin of this available torque, but this extra torque is available to counteract the forces users will place on the system as they try to control the recoil. This new motor also eliminates the need for a gear set, and we redesigned a new mounting disc that connects the linkage to the motor and allows for the recoil to be variable. The linkage system now consists of a rod end linkage instead of a custom-made system. This simplifies the components and ensures alignment. With this design, we're able to maintain a rate of fire of over 850, have full force variable recoil anywhere from 0 to 100%, and this entire system can be built and assembled for about $1,000. Next slide. If we go on to the part breakdown, the motor is housed outside the gun, but within the ammo can, not shown here. It then connects to the recoil disc. This recoil disc has a slot, and the distance upon the slot changes the amount of recoil the user feels from 0 to 100%. Connected to that is the rod end linkage. This linkage is able to pivot in all degrees. Attached to the linkage is the slider and carriage. The slider and carriage provide all the alignment and structural support needed. A connecting rod then connects the slider carriage assembly to the handle assembly. And next slide. So in the top left, we can see a top-down view of the linkage assembly. It is meant to be aligned. However, due to the manufacturing and installation, alignment may not be perfected. However, this is mitigated and counteracted by the pivoting capability of this rod end linkage. On the top right, these are the three parts consisting of the connecting rod. These are meant to be easily manufactured in a machine shop and welded together. On the bottom left, the motor needs to sit on standoffs. This is to allow space to have the tools required to loosen the fastener and adjust the recoil on the recoil disc. And then finally on the bottom right, we can see that the entire assembly with the motor housed within the ammo can. Next slide.
The requirements for this design presented by the museum were all met by this final design package. Just a couple of the key points we wanted to take away was that it fit in the required space, it met the full force variability from 0 to 100%, and it was safety was ensured throughout the design to ensure the safety of the user. Next slide, please. In conclusion, the design considerations that impacted us the most were the pandemic, as our team was unable to utilize either UCCS or the museums to prototype a design. The design was broken into 3 phases that moved from that rotary slider that moved the mass to a linear motor that moved the handle or mass to our final design that was just outlined above. The requirements for the museum were all met, and the museum was highly satisfied with the progress made during this design phase. Thank you for watching.
Hi, I'm Ryan Janitel. The National Museum of World War II Aviation has partnered with the University of Colorado, Colorado Springs, to allow seniors in the Mechanical Engineering Department a chance to work on solutions for real-world problems. The museum and its representative, Vern Patterson, want to create an interactive display simulating being a gunner on a B-25 Mitchell during a World War II bombing mission. The scope of this senior design project is to create a museum-quality replica of a Browning M2 50 caliber machine gun. The replica will also house a mechanism that will be designed concurrently by another team to simulate the physical sensation of recoil. It must also be able to interface with future projects, such as software and hardware needed for video game-like interactions. A successful completion of the project will include complete computer-aided design files and a safe working replica complete with a stand and room for expansion hardware, such as controls and speakers. Additionally, the museum has requested that gun sights unique to the aircraft version of the .50 caliber be recreated to contribute to the realism. The replica will also feature an authentically simulated charging handle that will arm the recoil mechanism and provide a signal to the future software integration. A large part of the learning experience will be research, time management, and fabrication. As a nonprofit organization, the museum also has limited funds to be able to complete this project. Accordingly, labor must be provided by our team or at no charge from a business that supports the museum. Materials will be purchased and provided by the museum after a list is completed and submitted by our team.
Hi, I'm Jason Wade. I will be talking about calculating the recoil forces that the replica may experience while providing realistic sensations, providing a workable budget for both labor and materials, and creating a safety matrix to identify and rate hazards associated with the eventual working replica. Since this will be a dynamic model that is expected to simulate realistic recoil forces, those forces must be calculated. The forces are divided into two parts: the force experienced by the bolt as it moves within the receiver of the replica, and the recoil forces that the operator will feel as part of the simulation. The forces can be calculated by balancing energy and momentum. First, the mass of the bolt inside the receiver must be measured or approximated. Since the genuine M2 bolt was not available, the dimensions of the bolt were researched, and then mass was calculated using the density of steel. Using a volume of 60 cubic inches and the density of steel at 494 pounds per cubic foot, the mass of the bolt was determined to be approximately 0.533 slugs. Once the mass of the bolt was calculated, the recoil spring force needs to be estimated. It takes approximately 50 pounds of force to compress the recoil spring in about 8 inches. This results in a spring constant of 74 pound-feet. Balancing momentum, kinetic energy, and potential energy, along with the researched mass of a real Browning M2, the bolt force was determined to be nearly 200 foot-pounds, and the operator would feel 44 foot-pounds. The bolt force is especially important as it will be used to determine the strength of materials for the replica. After our team decided that the replica will be made from aluminum and the stand from steel, a budget needed to be compiled to allow the museum to develop the funds for materials. Using 2 online sources for aluminum and steel, an initial materials budget was performed and came to approximately $700. The labor for the fabrication will be provided by our team, so no expense is needed for external work. The plan for this replica is for it to be used by the general public. As such, it is paramount to keep safety in mind for protection against injury. A brainstorming session was conducted to determine hazards and a way to quantify them so as to create mitigation parameters to neutralize those hazards. It was determined that on a scale from 0% to 100%, our design was only rated as 14% hazardous after mitigation.
Hi, I'm Ryan McGinnis. I will be talking about time management and the design process. Long-term team projects become very complicated. It becomes very important to keep track of which team members are working on a particular task and when each task is due. A Gantt chart, such as the one shown, is a useful tool to keep tabs on all of the individual portions of the project and how they fit together towards the final goal of completion. To be able to create a workable Gantt chart, the deadlines for major subcategories must be known in advance. These deadlines are chosen ahead of time since they cannot be missed. Working backwards from these hard deadlines, time can be allotted for each part all the way back to the present time. This gives us the ability to be able to give more time for complicated processes by setting soft deadlines. Soft deadlines can be changed as long as the Gantt chart is kept updated to show transparency and the deadlines that cannot be missed. One of the most important elements of the engineering process is design. There are many different design processes. One thing they have in common is a team meeting where ideas are presented and they are rated on feasibility of engineering principles. In the end, different ideas with the same ratings are voted on so the team can take ownership of the design and begin to move forward. We chose to use a design process that began with a brainstorming process to identify criteria and solutions. This ended with a vote on each vital area. The final design for the replica included having the receiver and barrel with shroud made from aluminum and the stand made from steel. The replica would have a removable threaded barrel for maintenance and portability. Fabrication would include welding the upper and lower straps and the front plate to the receiver sides for strength, whereas the back plate will be bolted together for serviceability. The charging handle plate and arm would be machined from aluminum, while the handle axle will be a steel bolt. The charging hand grip, the trigger grips, and the gun sights will be fabricated using additive manufacturing, commonly known as 3D printing. The stand would be made of steel for strength, durability, and to keep the center of gravity for the assembly as low as possible for safety. Lastly, an ammunition box attached to the stand to house the controls and speaker.
Hi, I'm Connor McCalkins. I'll be talking about the importance of prototyping and computer-aided design for our project. Based on the design requirements from the museum, our project has the parameter of having the look and feel of an actual Browning M2 machine gun equipped with aircraft sights. This fixed metric allowed us to be able to take dimensions from sources on the internet and actual measurements from dummy guns at the museum and use them for our replica. The museum allowed us to climb inside the North American B-25 Mitchell to take those measurements. After creating scale drawings with appropriate dimensions, the next step was to create a prototype from an easily manipulated material such as cardboard. After the cardboard prototype was completed, we took it to the museum to compare it to the other replicas, but it was about 25% too big. This shows the importance of having testable physical prototypes, even though if it was just out of cardboard. Had we not made the prototype, our error may have not been discovered, and we would have produced an oversized final design, which would not be acceptable. Additionally, modeling the prototype allowed us to see where the recoil mechanism would be placed within the receiver. One of the museum requirements was for a full set of computer-aided design files. Using SolidWorks, a commercially available design software suite, every part for the final model was created virtually. The final part count ended up being 39 pieces, and are all together in one assembly.
Hi, I'm Evan Sauls. I'll be concluding this discussion of our senior design project. The final few months of our project was interrupted by a serious manner. The COVID-19 virus has spread around the globe in a pandemic that interrupted every facet of daily life. Our last day of in-class attendance was Friday, March 13th, 2020. Since then, we have worked virtually, conducting meetings via online applications, all the while continuing to produce a final product for our sponsor, the National Museum of World War II Aviation. Our final product includes complete computer-aided design files for the entire replica, integration for a recoil-producing mechanism, and hardware for a future video game software package, and a 52-page final report detailing our research, time management, and conceptual design process. We have planned to completely fabricate a safe, working replica complete with a stand and room for expansion hardware such as controls and speakers. Unfortunately, since we were not able to have access to the campus machine shop to complete this task, with our sponsors' encouragement, we compensated by creating a step-by-step build manual for a future team to produce. While this was disappointing for us as we had looked forward to this build for 7 months, it was understood by all parties involved that we could not accomplish our final task. However, we will take away this valuable experience for the design project and start our mechanical engineering careers with this knowledge. Thank you for watching.
Good afternoon, ladies and gentlemen. My name is Eric Searles. With me today, I have Connor Opel, Daniel Benishek, James Tedeschi, Ali Sines, and Connie Guzman. And together, we're the team assigned to the National Museum of World War II Aviation here in Colorado Springs. Specifically, our team was tasked with working on the Link Trainer modernization project. So on the screen here, you have two pictures, and the left picture is actually the original Link Trainer housed at the museum. A little background on the Link Trainer. During World War II, the Link Trainer was used to train pilots on instrument flight. It did this by using a vacuum to control a rotational and bank and pitch system so that the pilots who were training on this felt like they were flying a real aircraft without actually jeopardizing any real aircraft in the process. During World War II, thousands of these units were made, but the museum is very proud because this unit on the left is actually the only functioning original unit left in the world. That being said, even though the museum is very proud of it, they can't really use it as an interactive feature at the museum just because it is antique and a little bit harder and more valuable when it comes to working on it. So on the right side, you can see the museum's first attempt at modernizing the Link Trainer. Unfortunately, this modernization didn't really live up to what they expected, so our team was tasked with taking the good from both the original and the modernized Link Trainer and creating a newer Link Trainer, specifically a Link Trainer base that met all of the museum's requirements. That way, the museum would have one more educational tool for its tool belt. Now, to do this, Connor will actually follow me, and he will talk about our project specifics.
Thanks for that introduction, Eric. I'm going to be going over our requirements matrix. So at the very onset of our project, we found it important to sit down and develop a list of requirements that we needed to meet with our design. And so we did this by way of this matrix here. On the far left, you're going to see our main requirements. And then as you move further to the right, you're going to see the derivative requirements from the main requirements. Each of the sub-requirements were given a priority. And these priority levels were later incorporated into our decision-making process where we ended up boiling it down to our final design. So looking at our main requirements, the first two that we looked at, they were the most important, was the rotation and the bank and pitch system. We talked to our sponsor, Vern Patterson, and he gave us a lot of the specifics from the original Link Trainer that we need to incorporate into our modernized project in order to make it as close to the original Link Trainer as possible. Next, on the main requirements, we have the mobility. We wanted to be able to pick it up with a forklift and move it around the museum just to make it easy for them. We also wanted it to detach from the fuselage. And then we also looked at the safety. It was very important that it was a safe piece of machinery because we knew that there'd be kids riding inside the modernized Link Trainer, for that's what the museum wanted to ultimately use it for. And then lastly, we looked at the maintainability. We wanted it to be a piece of equipment that the museum could take apart and disassemble very easily. So moving on to the vacuum system, I'm going to hand it over to Daniel.
Alrighty, so now we're going to dive into more of the description of what we chose as our final design. So From here on out, we're going to be throwing around a lot of things, and we've already done it a little before, pitch, bank, and yaw. So if you're familiar with aircraft, you know what those terms are and what they mean. But just in case you're not, I have a really cool model plane here. You guys know what it is, bonus points. Anyhow, so when we talk about pitch, we're talking about moving our plane or a fuselage for the link trainer up and down like that. Talk about roll or bank, we're talking about moving it like that. And yaw or rotation, side to side like that. All right, so now I'm going to detail the pitch and bank system that we chose. And the system we chose was to emulate the original link trainer system. So this is a group of 4 bellows being controlled by a vacuum motor. And the reason we went with this is because the museum is very familiar with this system already. You know, they've restored an original system like this on the 1943 original link trainer. So this will make troubleshooting very easy. Further, they already have the capability to manufacture some of these parts like the bellows in-house. So this will make maintenance very easy, very cheap, and very simple as opposed to something like linear actuators. Where our design differs a little bit is that in our use of the valves. So the original system uses mechanically actuated valves, and these work, but they're kind of hard to find these days. And it's also hard to get power to them through a rotating base. So instead, we went with off-the-shelf electronic valves. Our system uses 6 of them. 4 of them are open, what we call open-close or switch valves. These are very simple valves that you apply power to them, they open, take away power, they close. These are used to control how or which bellow air is being pulled out of. The other 2 valves are flow rate, what we call flow rate control valves. These control the amount of air being pulled out of the system. So this will control the bank or pitch rate or how fast the fuselage is moving. And so you can see a block diagram of that on the left there. And then on the right, you can see how we shuffle things around to make it all fit in our space requirements. That's the pitch and bank system. Now I'll hand it off to James to talk about the yaw or rotation system.
So to create a modernized link trainer that was safe for children to use, we had to develop a rotation system that didn't allow for any vertical or lateral shifts during operation. Essentially, that meant we had to prevent a wobble while the fuselage rotates. So we designed a system consisting of 2 tapered thrust bearings holding a rotating shaft to the system's frame. As shown by this middle image here, the bearings, which are held in compression, keep the shaft level. The top bearing's inner run is braced against a steel ring that's welded near the top of the shaft. The outer run of the top bearing then slides onto the inner run, and an outer casing is positioned to hold the assembled bearing. 8 support pins are inserted into the casing, 4 on top, 4 on the bottom, as shown in the image on the right here. The 4 top support pins hold the top bearing's outer run in place. The outer run of the bottom bearing is then placed against the 4 lower support pins. Then the inner run of this bottom bearing is inserted to complete the bottom bearing. A tensioning nut is then placed on the threaded portion of the lower shaft and tightened to keep the bottom bearing in place, thereby holding this whole system together. Once the system's assembled, the 8 support pins will hold this rotation system to the frame using bolts and brackets. And this pin and bracket and bolt design was chosen because it makes the whole assembly easy to disassemble and reassemble as the museum requires. So on the image shown on the right here, a pulley, shown as the blue circle, is attached to the lower end of the shaft, which connects to the rotation system's motor. Allie will now talk about the motor that will drive this rotation system.
Thank you, James. So when we began this project, the museum provided us with a DC electric motor out of a wheelchair. And in order to power this, we wanted to go from a standard wall outlet to a DC voltage controller. To do this, you have to run it through an AC to DC converter. And then once you get to the voltage controller, that allows us to reverse the direction of the motor so that the whole rotation system can go from counterclockwise to clockwise. It also allows us to control the speed of the motor based on the amount of voltage that is going into it. Unfortunately, due to COVID-19, we were not able to construct our project. So I'm going to hand it off to Connie to talk about the SolidWorks renderings that we did of it.
All right, so since we weren't able to produce a physical product, we did create the SolidWorks drawing, and this first drawing here on the left-hand side shows the front corner view of our complete base. So as you can see, there's 2 halves of our base where we have the lower half, which is our steel frame contains our rotation system, or the system that creates that yaw motion. And then we have the upper base, which contains our bank and pitch system, which is the vacuum system that Daniel talked about earlier. In this picture here, we can see that the upper half of our base, and you can see the top view of our vacuum system. You can see the bellows, the vacuum, the switch valves, and then the flow control valves as well. And we can see the placeholder for the U-joint, which connects directly to the fuselage. Here on the lower half of the base, you can see the bottom view of our rotation or yaw system. You can see the blue pulley that is attached to the lower half of the shaft that's also connected to the motor, which is going to drive our rotation system. And in this last image here, we wanted to incorporate that capability of mobility. So what we did was we added 4x4 steel stock on the bottom, like as little stilts to be guides for our forklift, so that the museum can move it into different locations of the museum. We did also attach a safety latch up on the top right. And here, this is meant to secure the fuselage when visitors are entering and exiting the fuselage cabin, and it'll keep it stable. And then we did also incorporate safety catches on top of this, on the wood frame, which will, in case of the fuselage did drop onto this wooden upper half of the frame, it would keep it stable and from tipping over the left or right side or any other angle, and also to reduce the damage to both halves of the equipment so it can be repaired. Overall, this was the final product we were able to create for our sponsor, and it's just a SolidWorks rendering, but this is what we have. Thank you for your time and your interest, and if you have any other questions, we will be having a Q&A on May 8th.